I am very excited to introduce Anthony and Peter of Tencent today, who are going to be talking about the Windows Subsystem for Linux Reloaded, and let's do better fuzzing. I have been working with the LXSS team for a very long time, since before it was launched, and I am really looking forward to hearing this talk. Anthony is a security researcher from KeenLab and Tencent. Previously worked on Android kernel, Linux, and recently switched to Windows kernel security research. Thank you, by the way, for doing that. We're focusing on mitigations, WSL, and advanced fuzzing techniques. And Peter is no bio provided, which I think is even more mysterious and fun. Please welcome them to the stage and have a lovely morning. Good luck, guys.
Okay. All right. Good morning, everyone. Thank you for being here so early in the morning with us. All right. Today we are going to talk about WSL, which stands for the Windows Subsystem for Linux. My name is Anthony. I'm a former security researcher from Tencent KeenLab. And I used to work on the Linux and Android kernel before, like she said. And so just a fun few trivia about me. I speak French and also I love Japanese culture. So if you want to chat about this, you can contact me or talk to me later after the conference. Here's Peter, my other colleague, and he's a senior researcher at Tencent KeenLab. I think probably most of you already know about him, so I'm not going to introduce him too much. All right. We've got a few things to do on the agenda today. So basically, I'm going to introduce the WSL first. Then we are going to move on to fuzzing, what Microsoft is doing, what we have been doing. And then we're going to talk about one bug which has already been fixed, because it's not fun if there is no bug doing fuzzing. And Peter will move on to the second part, where it's going to be more about the reflection, the feedback, the mindset. All right, let's get started. So for the people who don't know what is WSL, it's basically like if some of you worked on Linux, on Windows before, you basically had Cygwin, which gives this emulation compatibility. But now you don't need to do it now. Microsoft did a very good job in the kernel, and they introduced like WSL, which is a compatibility layer for Linux application to run on Windows. And this is really cool. It also emulates like the file system. So basically, you have two main important file systems here, which is volfs and drivefs. The volfs is the Linux part file system, and the drivefs is where you can actually access all the Windows files from Linux, from Bash. So why is WSL so great? It's great because like you don't need like now to have these wrappers with Cygwin. Like it takes a lot of resource like to adapt, like to change things, to do a lot of tricks. And it's also much faster like than running a VM and restarting every time the VM. But there's still a few stuff in progress. Like not every Syzkaller is implemented in WSL. There is some service which is missing. So you won't be able to run like every Linux binaries, but most of them you can run them. So if you're really interested into this, I would suggest like take a look into it. It doesn't take much of your time. It works pretty well. All right. OK. The first thing to talk about is like how WSL works, because like if you're going to fuzz the kernel, we need to know like how is it working in the kernel, and also it's very amazing to know. I mean, very interesting to know how the mechanics is behind it. So basically, WSL uses a new concept which is called a Pico process and a Pico provider. I will explain a little bit more in the next slide, but basically for Linux on Windows, the Pico provider here is the driver lxcore.sys. The other one is not really much used, or the core logic is in the first one. So here's like a simplified diagram from the Microsoft website, which explains what it is. What is a Pico process? So on the left side, you have like the normal NT process. We're not going to delve too much into like protective process over stuff like this. And there's this new concept, which is the minimal process. Basically, it's a process where you don't have anything inside the address space. It's just an address space. And what it does is just, it tells the kernel, don't come manage me. I'm going to do everything myself. But the kernel still do some stuff like scheduling the threads and allocating memory inside of it. I'm not really sure exactly what the minimal process purpose is in the Windows kernel, but I know like in Hyper-V we use it like to isolate process in VBS. And basically, the Pico process is not much different. It's just the same thing, but it has a Pico provider. What is a Pico provider? This is a driver in the kernel, and it allows, so if you have a Pico process, then the kernel, when you're doing an interruption from user land or an exception, then the kernel can intercept these interruption exceptions and redirect them to the Pico provider. And then the Pico provider will provide the functionality that you need. This is very great because if you want to add like new syscall, like the Linux syscalls, you don't need to modify the syscall table. You can just put your driver, and then the driver will just intercept the syscall and give the functionality back. All right. So that's pretty much about WSL. I'm not going to delve too much about it. Why is it interesting? So the first thing is like I noticed like Microsoft said like they clearly stated their intent that they want to attract more Linux dev into the Windows world. So we can expect in the future probably a lot of people will use this WSL. And this is a very interesting target. It has a lot of entry points, a lot of new code in the kernel. And obviously, Microsoft, they are not like dumb. They are smart people. And they didn't re-implement everything from zero. So most of the functionality is just provided by the anti-kernel. But of course, when the syscall semantic doesn't match with the Windows kernel, they have to re-implement from scratch. For example, like the Unix socket, shared memory, this kind of stuff. And what I wanted to say, like, because like they use a lot of the NT features to implement it, it doesn't mean like there is no bug. Because like a lot of re-engineering inside the kernel, like for the memory part, like do you know like for example the Pico process, it doesn't use like the 64 kilobyte allocation anymore, granularity, it uses 1 page. I didn't know that, but no. And so yeah, there's a lot of re-engineering the kernel, and what I want to say is like it's very hard to know all the side effects that can potentially affect the security of this new technology. And yeah, why is there no other public LP of WSL? Why? This is a very interesting target. Is it too hard? Is it because Microsoft did a good job, obviously? And yeah, or maybe just nobody tried to fuzz it. So this is a very interesting target for these reasons. And if you want to know more about WSL, you can check Alec Ionescu work on it. He's a very great guy. He did a lot of research for it, and you should check his slides. The other thing like I would like to mention about WSL, which is very interesting, is that I noticed like this is medium integrity level. It's not sandbox, so it's a very juicy target, lower profile than other like edgy. And the very, very cool thing about WSL is like there is this ability to communicate with the Windows system directly. So basically a Pico process is just a Windows process. You can modify the Windows file system, so it's powerful. And the thing which actually surprised me is like if you have embedded like Windows PE executable code inside the Linux binary, and then you just create a file on the Windows file system, put it there, and execute it, it will execute it. It's kind of real, but well, yeah, that's really nice for us. Like if you want to do some exploit, because like the Linux and the Windows part, we can communicate via IPC with standard input or socket or IPC, and then from there, because like when we are doing exploit dev, we sometimes need like some primitive, like some spray, some target in the kernel. And the ability for us to be able to switch between these two components allows us to have more primitive. Like from the Linux part, you could like call the NT API and then spray in the kernel some object, and from the Linux part trigger some, I don't know, some bug with overwriting, and you will get your shell easily. So the first thing like we need to do like before even doing any fuzzing is like kind of grab a sense of the attack surface. So basically here is a screenshot from the Lighthouse plugin for IDA. And what I wanted to do is like check a little bit like where is the complexity here. So you will notice like most of them is about VFS related, VFS for virtual file system, and the new functionality, for example, IPC and polling. The other thing I noted is like most of the functions have less than 10% of complexity, which makes sense because most of the functionality is provided by the Windows kernel. And there's a lot of syscall. There's almost 245 of them. Some of them are not implemented. They just return an error code, but still a lot of syscall entry points in the kernel and a lot of bugs that could be found potentially. So Microsoft did some job here on the fuzzing. They use Trinity from what I found on the web. Like they have leveraged it, and they have found a lot of critical bugs inside of it. And so for those who don't know, Trinity is one of the earliest fuzzer for the Linux world. It's just a black box fuzzer, a little bit naive, just doing some generation. But it's a little bit more intelligent than naive. It tries to feel like the right input, like the right file descriptor when the syscall is expecting it, but not more intelligent than this. And I kind of can understand why Microsoft chose it, because it's very easy to bootstrap it, to run it on WSL easily. You don't need to configure anything. You just run on your 1,000 servers, and for 1 week, and you just hope some bugs pop out. I also saw that they probably are going to put some kernel coverage inside Trinity, because they have the kcov.c, which is the file in the Linux source code which provides the code coverage. This seems awesome, but well, we don't exactly know when they are going to do it. So that brings me to the problem, like, we should not, Microsoft should not rely on Trinity only, because like the project has not been much developed, been committed on the GitHub for quite some time. And if you compare with like equivalent fuzzer of like our time now, like let's say Syzkaller, you can see like the list of bugs Syzkaller is finding is much bigger and more recent than Trinity. Like it finds it like every week, I don't know, every month probably. And the other thing is like when you are trying to scale your fuzzer and deploy it, like the problem with Trinity is like it messes up with your file system and environment. So don't run it on your host machine or it's going to be messed up. But the biggest problem with Trinity is about like its lack of intelligence. It doesn't have any more refined input. Like if the argument is a length, then you cannot compute the length of the other one. You need to do it manually. It's a lot of manual work to code it. The checksum, the same thing. And it doesn't have this knowledge about internal state connection. Like when you're fuzzing kernel, this is very important. Like when you move from one state to another one. Yeah, exactly. So normally, usually, I mean, nowadays, like fuzzers are very good. They have a lot of very nice features. Like for me, like a fuzzer should make the life of the researcher much easier, because we are kind of lazy. But so what I'm expecting from a fuzzer is that it's able to monitor it, to deploy itself very easily, able to catch the crash, extract it, and probably symbolicate it, get some information from it. And Trinity is not doing that. There's also the tooling. It's very important. Like if you don't have any reproducer, how can you reproduce your bug? It's cool, you have a crash, but you will probably never find the origin of the crash. Then the most important thing is the knowledge, the learning, the intelligence. And with Syzkaller, it has this ability to be evolutionary. Like when usually we get some metrics when you are fuzzing. Like in our case, it's code coverage, but it could be like return error codes, which tells you like where exactly in your fuzzing process are you, which area of code are you exercising. And Trinity doesn't have this. It's like dumbly fuzzing everywhere, putting noise everywhere, but it has very low probability to find bugs like this. And the last thing is like about collaboration. Because Microsoft, they have a lot of servers, they're fuzzing a lot of servers. If you use Trinity and you don't have this, suppose like you manage to get the knowledge from Trinity, you still need to be able to back propagate this knowledge to the other fuzzer. And this is why you should not use Trinity for this kind of stuff. So I'm going to talk about Syzkaller now. This is the fuzzer we have leveraged for our work. Big thanks to Dimitri and his team. They did a very good job for this. We are committing every day on the GitHub page. A lot of features are coming every day. So yeah, here Syzkaller has pretty much all the qualities of that I mentioned before about the modern fuzzer, and it will improve your productivity a lot, like a lot. And the best thing about it is platform agnostic. You can, for now, it only runs for Unix systems, but you can potentially put it everywhere. Here is like a bigger overview of Syzkaller, very simplified, taken from the GitHub. So how does it work? Like You have a sys manager. This is like the big guy who is going to manage the VM, deploy them, get the feedback back, and send it to all the workers. So on the bottom, you have the VM, and inside of the VM, the manager is going to deploy all the fuzzer files via SSH. And the first important binary is the sysfuzzers. It's where all the logic happens, all the core mutations, the evolutionary thinking. It happens here. The executor, like the name, is just an executor. It just executes what the fuzzer tells him to do. And basically, every program it wants to fuzz, the fuzzer sends it via shared memory, and the executor will just put the object, the arguments in memory, and then execute the syscall one by one. So this is a kind of a good way to do it, because then you don't need, you have some kind of decoupling, and it helps like to find when you are modifying syscaller, then it's easier to find mistakes, and also you don't need to worry too much about like how to mutate the data, because it's independent, like very generic. As a comparison, you can see like this is a Trinity code for on the upper side is a Trinity code like to generate the socket arguments. It's clean, but it's a lot of manual work to generate this. Like you're spending a lot of time just doing coding your description, how to generate the syscalls. On the bottom, you see syscaller. It's very simple. 4 lines. I already have 4 syscalls. And the problem, like this is nice because it improves our productivity, but there is some downside about it also. Like if you want to have like some dynamic behavior at runtime, like you want to, let's say, you execute a syscall, you get one result, and from this result, you want to be able to choose like if you want to execute another syscall. This is pretty hard to do with Syzkaller, but it's still possible. All right, this is pretty much it, and so we are going like to say like all the problems all the steps we made to port it into Windows. There is a lot of stuff to say. The first thing is like there is no code coverage for Windows. This is a big problem because Syzkaller is based on this evolutionary strategies. It doesn't have code coverage. It's not going to work very well. Then there is the deployment. For the deployment, we just use QEMU because it's very easy to deploy. And the portability. For portability, what is great about Syzkaller, like I said, like you can run it everywhere, it's because it's done in Go, and Go can cross-compile pretty much easily. And the last stuff is just access permission, which you can configure on your machine, because otherwise, if you SSH into your machine and you run bash, then it will not do it because you are remote launching kind of a shell. So we're going to address like the first problem, which is like the most important one, the code coverage. And there was a couple of solutions like we were thinking about. There is the QEMU TCG, the translation part of QEMU, which you can do it. It works well, but it's very, very, very slow. And yeah, there is some hypervisor tricks, but we don't want to code like the hypervisor from zero. And what worked best for us is the hardware technology IntelPT. And it just so happens that there is already a published project about it, which uses IntelPT, the KAFL project. IntelPT has much lower overhead than all the previous mentioned solutions, and it doesn't have so much side effects. For example, if you rewrite the binary, you need to worry about all these kind of side effects. So basically, we use KAFL, and what is great about KAFL is that it's on Linux, and you don't have to modify the code too much. It's written very well. You just have to modify a few stuff. There is a few things that needs to be said. Like this is not a perfect solution because when you use IntelPT is not going like to get you every basic block address in memory. What it does like is going to do a compressed version. It will say of the control flow. It will say like if a jump is taken or not. Some kind of very compressed format. The reason why is because it generates a lot of data, like if you need to trace everything in the kernel. And what we do, like we don't want to trace everything, so we just set a CR3 registers to only track our own process and also specific address ranges. And when it gets so this flow of packets, because it doesn't have like precise information, we need to rebuild this call graph using capstone. So KFL is like disassembling it, and there is some imperfection sometimes when disassembling it. So you might miss some basic block, but it's okay. We can deal with it. It doesn't change much. The other thing is like KFL can only track one CPU at one time. It doesn't support multi-threading, but you can change it. This is important. Why? Because in the Linux code, it's different from Windows. It doesn't have like so much asynchronous work where you can just run one syscall and then it will come back to user. There's a lot of blocking syscall, so you need to be able like to thread it, and you still need to be able to get the coverage at the same time. And the last thing which is great about KFL is KFL, basically, it goes via the hypercores, and the hypercores have basically the same semantic as what Syzkaller is using to get the coverage, like starting, stopping, etc. So, in practice, this is what we get, like we are doing some coverage. This is from my laptop, like with, I'm running 3 VMs, and you can see like this is not the ideal, like I'm running like 96 execution per minute, like basically a little bit more than 1 execution per second. The problem is like the context switches are not cheap, like he mentioned yesterday in the Hyper-V talk. And there's some kind of overhead with WSL. When we are fuzzing Windows, we get higher speed from this. But it doesn't matter because what we want is just, we want to get the corpus. This is what's really important and matters for us for the mutations. And then we can just run Syzkaller in black box. The speed is pretty okay, and luckily, there are quite some bugs actually. So this is the only bug that got fixed, so I can show it to you today. You can see the code is pretty much simple, very obvious bug, but I'm not sure why they didn't catch it actually. You can see that we are using the AF Unix socket. This is the new code in the kernel. Yes, we can expect to have bugs, but here is very simple. Like we don't even need to raise anything, no raise condition. But we have a while loop here. The while loop is important, like if you want to get the crash. So basically, when you get the crash, this is what I got like when it crashed. Like I got the kernel security check failure, and I saw this in 29. And at the time, I didn't know like really much about the Windows kernel. But actually, when an exception, something bad happens in the kernel, when it's doing a check, it's going to do an interruption. This is what happens here. And like I said, you can see here that we are crashing into the VFS. Like the VFS has a lot of new code and potentially a lot of bugs. And if you analyze like the bug check here, the bug check here is actually of type 0xe, so 14. And if you check up on the MSDN, it just says like the reference count for an object is invalid. So basically here we're kind of having a corruption of an object, maybe an arbitrary, right? We don't know that for sure. But yeah, that's already very helpful. So this is the surrounding code around the bug. And so at the beginning, it's doing an add, which is kind of weird for those who don't like read assembly. But basically, it's going to look up before our object in memory. It's like a subtraction. And it's going to test like if RAX is 0 or not. RAX, which I assume is the reference counting. And if it's not, if it's not 0, then it means like something bad happened. All right. The first thing, so this bug is a heap bug. The first thing to do is to enable a special pool. And when you enable a special pool, you get a lot of these patterns that we researchers love about it. It looks like kind of a UAF, but it's not a UAF. Basically, special pool is a special debugging feature which allows you to find like heap overflows, underflows, and even UAF. And when you enable a special pool, you can see the address of our object is not at the beginning of the page, it's near the end of the page. This is the object, the second picture. The first part is what actually is being dereferenced in the code. And because it's 40, 40, 40 and not 0, it's going to crash. And with special pool, it's going actually to allocate our object at the end of the page. And basically what we can see here is like, it's trying to reach out to the beginning of, before our object, kind of thinking like, okay, this object is an embedded object and there is a bigger structure surrounding it, but there is no bigger structure here. So actually, it's an out-of-bound read. Is it exploitable? well, actually, it turns out it is exploitable. So here is like a pseudocode from IDA Pro. It's going to be much easier to read than just assembly. And in red, the VFS file object class dereference is taking our out-of-bound object, the v2 argument. And if we trace it inside inside this function call, I didn't put a whole code because it wouldn't fit here. You would see that the square in red, there is a v9. And if you take the time to read it, you would see that v6 is being controlled. And we actually can skip all the checks before it and reach this function call. So basically, we can call any functions in the kernel now. We have PC control. But is that the only thing we can do? No, it is not. It turns out if you go down, there's a lot of other primitives there. You have like an arbitrary write here, not a fully arbitrary write, just a little bit constrained. You can write a 0 anywhere in the kernel. It's a pretty powerful primitive. You can turn it into an UAF, or you can misalign some pointers in the kernel. And at the end, it's also going to X-free your pool. So you can basically free any arbitrary object in the kernel also. All right. So there's a lot of primitive. But in this slides where I'm not going to talk about like exploiting the bug because I didn't have time actually to do it. But also like the talk is more focused about the fuzzing ideas. But this is how I would do it. Like, so we know our object is from a non-page pool. So it's pretty easy. There is a lot of resource on the web which says like how you can like spray on this kind of pool. And you can also find it your primitive inside the LX core, like I said before, or from the Windows API, kernel API. And basically, it's just a normal heap function. You just need to spread a lot of objects, to normalize the heap, put some holes, and then spread your target, your vulnerable object inside of it. And then it will auto-bound read the previous object, which you will control. And then, because this bug has a lot of very good primitive, you don't need to worry too much about it normally. So would this bug like be exploitable like on the newest Windows? Kind of yes. So there is no more public leak, but in our case here, we don't really need a leak because Bash is running as medium integrity level, and we could call the anti-API to leak the kernel slide. SMAP is not possible to be disabled, but like I say, we don't need it. And yeah, WSL is a very juicy target. It's not as much protected as the other high-profile targets. And so if you have a chance, take a look at it. Great. That's it for my part, and I will let my colleague Peter continue.
So hello, we're coming to second part, which will be a bit shorter, less technical, I guess, and we'll talk about more about mindsets and what we do after, for example, we try Syzkaller. So first, we take a reset a little bit and start from the motivation, because we are at BlueHat and Microsoft conference, so I found it pretty much related. For example, for us as white hackers, what motivates us to work in VSL. For us, it was also some personal reasons, because we have some background in Linux and Android kernel. So basically, we can reduce our experience, and reducing experience is really good because you save a lot of work, and at the same time, you learn from it, because it's you focus before on some targets. And so when you want to use this work to on the targets, it means you need to do something more generic. And so it learns you how to do more things more generic way, and how to learn from new targets and apply the knowledge backwards to target you focused before. So I think it's really good, but still we have VSL on our radar and to-do list about 1 or 2 years, but we're still not moving towards actually researching on it. But Microsoft come out, it's not beta anymore, it's service, so we get CVE and even bounty as part of insider preview. So it's really nice, and we're starting to focus on this a little. And as I told before, for me, it's a lot about saving my time and do things efficiently, so I like reducing work. And I was before working on WinP2K, so for me it was obvious choice to compare it to another subsystem, because WSL is also subsystem. And it's what this means that it's contains a lot of logic. It's not like you add simple one syscall, but you add 100 of syscalls. And in comparison to Win32k, WSL is smaller. But on the other side, Win32k even bigger. They implement a lot of mitigations. One of these, for example, filtering. So it can filter a lot of syscalls. So it's shrink attack surface a lot, which is pretty much good thing to do. But bad side of Win32k, it's pretty old code. But on the other side, they refactoring a lot, adds a lot of mitigations, tactical mitigations. It's pretty nice. On the other side, WSL, it's new code. And that means maybe some new bugs. Let's see, we want to check it out. And maybe it's because of new code, they apply some new modern engineering, so it will be much more safer. So we want to figure it out. And for me, it's my style of fuzzing is more related to states. I consider at least two types of fuzzing. One type is for data fuzzing. It's about you focus on parsing of some data structures in kernel. But state fuzzing is more about the sequence of syscalls, which brings some kernel components, some certain states, and you can mess with reference counters, with pointers, with flags, and cause some different kinds of issues. So in perspective of state fuzzing and WSL, it's very nice that basically everything is a file. That means it provides a lot of connections you can work with. For example, you have sockets, pipes, you have shared memory, which basically works over some files. And you can all this connect with one syscall. Basically, to one syscall, you add for example, two different file descriptors, and it do some magic behind, and maybe connect, maybe increase reference counters, connect them somehow. And this is basically my targets of interest, to cause some user freeze, type confusions, and usually I enjoy pretty much doing it by race conditions. So in WSL, we have about 6 different core objects. I think there are, I guess, a little bit more, but I focus on this work mainly on the core part, because I want to exercise if, for example, Microsoft did something pretty much wrong, or if something forgot. And very good on the WSL, it's already some public research because it's basically Linux. And on Linux, you have a lot of intense work about the fuzzing, and it's basically all open source. One of the things is Trinity, which is basically some kind of naive fuzzer. It don't bring you too far with fuzzing, but it's good to have it. Definitely, when I will go on some new product, I will try it. But on the other hand, you have Syzkaller, which is state-of-the-art fuzzer. It found hundreds of bugs, so we definitely want to try it as well. And as well, we want to try our tools, our fuzzers, our approaches. But not alone, but combined all together. And also about Linux, a good feature that's basically well documented. You can find a template for almost every syscall. You can find a template for every syscall. And even you can find the source code not for the WSL, but you can find the source code for Linux. And this is really interesting, because in Linux source code, you can see how some component is originally supposed to work. And this one, you can think, when you have some knowledge about Windows, what kind of troubles can Microsoft guys can get it working on Windows? Which kind of tricks they have to use, which can they forgot? And that's the part where we start focusing more on the bugs, more thinking how to find the bugs, what kind of type of bugs. And for this one, we will try enumerate the attack surface, as Anthony said. We try to look at as much supported syscalls as we can. And we try to somehow file them to some buckets. I usually do it by, for example, sorting out by component which they're working on. For example, by socket syscalls, by file syscalls, by pipe syscalls, by EPOL syscalls. And then I also draw relationships between the kernel components, which can communicate, and between the syscall, which basically connect them. And with all of this, it can be pretty naive to, for example, to take all the syscalls and fuzz it like this, because it's pretty much different. When you have usually a bug, you just need to connect maybe 5, 6 syscalls. And it's quite feasible to run these syscalls and do some kind of dummy fuzzing with these 6 syscalls. Basically, every fuzzer today doing some kind of dummy fuzzing. It's basically randomly invoke the syscalls and doing some random arguments. Some of them have some more sophisticated techniques, but at the end, it's the same. It's some kind of just randomly combining. And when you have just 6 of them, it's very easy. But when you have 200 and they do it at once, it's becoming exponential problem. And it's becoming highly unlikely to find something more deep. So what we do, we select some important things and also not focus on all the syscalls, of, for example, of socket, but only a few of them and try it out. So for me, it's after enumerating attack surface, is sorting out these targets. For example, what I think it can brings me more easiest bugs or the bugs I focus on most, for example, use at the phase or some race conditions. And for example, when I look at it briefly, I see that, okay, that's prominent are sockets, for example. There are tons of bugs, was before Linux. I do believe tons of bugs will be also in this Windows implementation. And the same for key or TTI. They have some pretty sophisticated syscalls just connected to them and need to involve some specific logic. And of course, virtual file systems, because Linux WSL on Windows, basically, they can reuse a lot of logic, just wrap the Linux syscalls to NT syscalls, just make simple wrappers. But for some components, like virtual file system, they just need to introduce bunch of new code, which can be really prone. You can find probably there are lots of bugs. Maybe depends on how they implement it, how solid they test it. And but for me, it was this kind of prominent targets requires a lot of work and do it properly. I don't want to do just dumb fuzzing. And to be honest, I try to do this work 2 weeks before this conference. So I want to focus on just this kind of connections and just core components to make it fast and just prove if I can find something with this idea. So for me, it was some kind of mandatory operations because everything on Linux is a file. So for me, it was just file operation, read, write, some file CTLs, also on sockets, some basic generic setsog operations. Also choose, for example, only 1 or 2 sockets, which is Unix socket and which is maybe TCP socket, but nothing more, not going too deep because I want to just focus on one area. And from my perspective, when I want to find some user phrase, it's about these connections and it's really interesting when you have some file descriptor and you can share it through some, for example, in Windows, you can share file descriptors through LPC. And Linux, you can do this well. You can do through sockets. Basically, there's this kind of feature of some file descriptor, and you can duplicate handle, or you can send it through the sockets. And it makes another reference counter for this file descriptor. So it looks kind of interesting and used for this one, totally another mechanism. So for me, anything which can basically share file descriptor is really interesting. And as I said, I skipped a lot of into depth some work about some specific components. I want to some generic stuffs. So I end up with this kind of diagram, which basically root of everything is file. And to file, it's kind of, for example, sockets can have the similar operations file or some shared memory pipes, and they can invoke on file this kind of IOCTLs or generic writes. And for example, for sockets, it's really interesting for me that you can create server and you can connect their clients, multiple clients. So this logic I want to also exercise. And for example, memory. I create the memory, but a lot of syscalls can use memory. Basically, you provide some buffers. So I use the memory which allocates, and I use it some kind of artificial file descriptor to just share in process of my fuzzing. OK, so I'm almost set. I know attack surface. I know what I want to target. I want to try it out. But before, definitely, I don't want to reinvent the wheel. That's why I was working with Anthony, and Anthony did before some job on this one that I can see, because when I have some idea, I can try it. Then I find nothing. And what I can learn from this one, basically not too much, because I don't know. Did I did good? It's hard to say. But when I have some benchmark, like a Trinity, like a Syzkaller, like MW fuzzer, or some different kind of fuzzer, I can say, OK, I'm totally off. I find something new. It can make sense or not. So that's why our approach is, OK, try first some state-of-the-art tools, some tools that already exist that bring some results, and compare to them. At first, there is Trinity, which we don't use because Microsoft using it a lot from what we learn and read from blogs. And also because it's a bit naive approach. For us, it's kind of similar like a dummy fuzzing. I mean, it's essential, but it's some kind of naive. And I don't think it can bring some deeper bugs. It's just more prone to take some low-hanging fruits. But I want something more deep or something more interesting. For this one, Syzkaller is really good because it has some good systematic approach how to do it. It can learn, and with time and knowledge, it improves basically by themselves. And in theory, it can do code coverage and this fuzzing arbitrary well. But Syzkaller, how to? Anthony already talked about, for example, that he do a lot of work on how to port Syzkaller. It was mostly about the scaling and how to utilizing it. But basically, this work is it's feasible to do. I mean, it's everything. I think is open source. You need to just connect it together, and with your experience to make it work. So you can have Syzkaller there, and also for code coverage, it's KAFL. I mean, it works pretty good. We use code coverage not only with Syzkaller, we use also with our tools, and it works fine. It's just like modifications. Every time depends on fuzzer use or some tool you use, how you will modify KAFL, for example. But OK, for some people, it doesn't work KAFL pretty well because maybe they don't have hardware. Maybe they focus on Hyper-V. And there, you cannot use KAFL because it's based on QEMU. And for example, Hyper-V, you cannot run in QEMU. So what you can do? First approach is just you check the status code. You check if this Syzkaller is successful or not. If it's successful ratio, it's OK, 70% of Syzkaller is going through good, and 30% time my Syzkallers are not so going well. I think that's a pretty reasonable thing to do when you're fuzzing. You don't want to do too much good, and also you don't want to do too dummy stuff. So some golden ratio is fine. But on the other side, no need to stay only on this one, even if you don't have KAFL or Intel PT itself. You can use WinDBG. But with WinDBG, it can be pretty much overkill to, for example, OK, I will trace every instruction. It can be pretty much slow. But what you can do, it's basically you can do it on basic block levels. It will be faster. You will not need any feature or some kind of commands specific to WinDBG. You basically, for example, what I do, that's extract IDA, all informations from some diassembler like IDA, all about the address of basic blocks. And then I generate so much mini scripts as number of the basic blocks. Basically, when I know that my break mode was a hit, I know that from that point, only several locations, then I go next. And for every of them, I have basically hard-coded next script, which basically set the breakpoints next time. So in this way, I can just walk one trigger the breakpoint and can follow just basic blocks until to end to some specified point or some return function. And in this point, it's faster and give me all I need because I'm focused on code coverage. But this code coverage, it can be kind of overhyped because the question is if it's so essential or it's not. My opinion, yes, it's essential. It can give you significant boost because it can speed up your fuzzing. It means that, for example, we have your fuzzer. And your fuzzer basically can fuzz something for a fuzzer is easier to fuzz some paths. So it spends most of the time to fuzz these paths, but some kind of hard-to-reach paths, it's not necessarily touched so often or even at all. And so for this one, when you have some corpus, which basically can reach, you have some database of some programs which can reach some code paths, and you have some unique subset of these programs, you can basically fuzz more uniformly through this space. And it makes exploring the search space of the basic blocks when you want, for example, as much code coverage as you want. It makes it feasible. It makes some system how to reach as most of them as you can in some reasonable time. Because when you do this at random, it's very unlikely you will do something reasonable at the end. And also, it's efficient when you do some kind of unit testing. I mean, you, for example, spend 1 week to getting this kind of good corpus, good database of files, which basically can exercise your codes arbitrarily well. But you change something in the logic, some in the syscalls, you make some fix or something, and you want to retest if this fix is good, is correct, and this new logic added new syscall, probably not added new syscall, but changes in syscall, it's really solid. It will be a waste of time to run everything from the scratch. But you can use this database of the programs, and you do it instead of 1 week, you can do it in 1 hour. And it's pretty much save time a lot, and it's far more efficient. And also another thing, when you do your own fuzzer, usually you're limited to your own knowledge. You think, OK, I want to go there. Maybe it's a good idea. That's nice. But maybe fuzzer can do it by himself and can find something really unique that you may be overlooked. But on the other side, code coverage, I don't think it's all you need. It can be really overrated. It's some fuzzers, for example, like Syzkaller, his backbone is code coverage. I mean, it's basically, in my opinion, finding the bugs. But Syzkaller is some kind of byproduct because it's not focused on finding bugs, it's focused on expanding code coverage. And by this one, it's more efficient sometimes to find the bugs. But pay attention, that's when you cover everything, it doesn't mean you find the bug. Also, race conditions is not direct the root cause of the bug. It can get you there faster because you can exercise certain parts which maybe the race condition is hard to find more often, but it doesn't guarantee you find the bug. So therefore, our target when we use code coverage is not a bugs itself. It's some good set of programs which allows us to exercise this code, these components pretty good. And so for that one, when you, for example, evaluate the code coverage, how, for example, if your fuzzer can work with code coverage, we usually found in 2 days we get reach some sweet spots, some maximum of code coverage we can get, and then just slowly increasing if it's even. So in 2 days, and you get everything what you need, that's fair enough, good for testing. But for me, even if I use WinDBG and it took me 1 week or 2 weeks, 1 month, I don't care too much. My target is this good corpus. When I have this one, I can reuse it for the future. But problem is when it's too slow and you are not sure about the fuzzer, it can be terrible for testing. You cannot wait, for example, one or 2 weeks just for retesting something. So for this one, you can use this at first, ensure that, for example, this successful ratio of your syscalls are relatively good. And for this one, you can get more code coverage and get more feedback and improve fuzzer. And it doesn't then matter if it's too slow, this coverage. Mostly it doesn't matter that you get this kind of information. But after you get this kind of corpus, you can learn from this one. You can extract the knowledge. And you can do some different things. But with Syzkaller, for example, it's kind of harder to do it because it's based on templates. And its logic is really centered about the code coverage. It learns from code coverage and improves from code coverage. So it's modified to Syzkaller to work more specifically. It can work, but then you limit the effectiveness of the fuzzer likely, because you have your own mindsets and the Syzkaller has own. So that's why you want to, for example, likely to make your own kind of fuzzer, or maybe some modification to existing fuzzers. But be cautious, this is double-edged sword. You limit it really to your own knowledge, which may or may not be good. So some experiment results what we got with Syzkaller, our approaches was about 6 and more bugs. It was about 8, but 2 of them was not too much related to our specific fuzzing. It's more likely that we do some chaos, and it was about memory management. It's about 3 bugs was security issues. 2 of them was RCE. 1 seems leak, but I didn't check it further. And 3 about DOS. 1 is null pointer, and 1 is tag overflow. The trap. So it's, but none of them we already reported because I said to it last. I did some kind of last moment for my part, so I need to get through them and make a POC and report, but some of them we already reported. So now you might wonder what is the best approach. I mean, because we talk about Trinity's naive fuzzer, Syzkaller is pretty good, and with knowledge you can probably limit yourself, and it's maybe you're not better than Syzkaller itself. And that's true. That's why you need to combine these approaches. For example, smarter fuzzer cannot spend too much time of doing dummy stuff like Trinity do, but that's at the end maybe a big mistake because there's some easy bugs maybe your smart fuzzer cannot find, because it's, let's say, too smart. And also, as for example, Syzkaller is more sensitive about code coverage. Maybe it cannot go too deep into some certain areas, but with more knowledge and more feedback, you can do some your own logic to hit certain paths and exercise it more in depth. So in my think, you need to experiment to combine everything, basically. But at first, it's common mistake that, OK, I will skip this one because a lot of people was doing the same, just doing these tools, and I think I can do it better. It's true that when you try the same thing as the other people do, I'm likely to get different results. But you can learn from it. And from when you learn the capabilities of these tools, the limitations, you can probably improve. But at first, you need to really learn from this one. So final slides about conclusions. At first, I need to say Microsoft's thank you. I really like how you communicate with researchers. It's really nice. You get the bounties. You get really some kind of passion. Sometimes I've sent the POC inside to trigger, and even though the people from Microsoft just talk with me and we're trying to resolve this issue, not like, OK, for example, if somebody send me some POC and doesn't work, and I have plenty of other works to do. So for me, it can be a big annoyance. And I spend 2 days and it doesn't work, and I will be maybe too angry. But they're not. They're sitting with me, they make it work, and it's good. And also, but on the side, you offer the bounties. But you have the state-of-the-art tools. You have the, for example, Syzkaller. But we use Syzkaller, and it doesn't seem that you use Syzkaller. But Syzkaller can be used not only for VSL. It can be used from WinFit2K to Hyper-V to fuzzing hypercalls, to fuzzing I/O ports, to fuzzing COM objects, LPC mechanism. You can use it basically for everything. And before, for example, for my set, if I offer bounty or this kind of cooperation with outside security researchers, at first I want to do it in-house, this open tool which is openly available, because it makes more challenging for them, and that's we more care. We do everything to our best, that we use public stuffs, and then we communicate a lot with other people. But overall, I'd say WSL is relatively OK. I mean, we don't do proper vulnerability research. I mean, for my set, I don't even open the binaries. I just try I know the syscalls of the Linux. I try to experiment with this one. I have some idea, and that's it. And I found some bugs, and also trying to find some bugs. But this barely scratches the surface, I think. So I think there is more, but relatively, it's OK. I was expecting it will crash more easily. I mean, for WinFit2K, once a point they have some good fuzzer, and I just touch WinFit2K at that point, just crashing everywhere. VSL, not. VSL is more stable. I think it's a good job. But as well, I think need to do some more work with open source tools. Really, you have the open source state-of-the-art tools. You need to just use them and scale. You have so much machines. I can, for example, have 50-core machine. I tested on this one, but maybe you have 1,000, of course. And this makes a really difference with these tools. OK, so thank you very much. And if you have any questions, please ask.
Thank you.